mofos. Today I'm going to be explaining why work is force times distance instead of force times the time that you have applied the force. Now in school, you would have already learned two facts. First of all, work is force times distance. That's the first fact, but you probably didn't intuitively understand why this equation is true. The second fact is that work is the change in kinetic energy, which is 1/2 mv squared. So I'm going to intuitively make you understand why the first equation stands true. I'm gonna give you an example. So we have a white block and we have a black block. Now the white block is still. So the initial velocity of this white block is 0 meter per second. And the initial velocity of the black block is 3 meters per second. So it is moving, right? So I'm just gonna draw a line here to separate these two. So let's say you applied a force to these two blocks and you apply the same force. The force that you apply, I'm gonna show in red. Yep. The force that you apply will be 1 Newton. 1 Newton. And you apply this for 1 second for both. Okay. And when you do this, the final velocity of these two blocks will be 1 meter per second for the white block and 4 meters per second for the black block. And you know that the white block will only have traveled 0.5 meters. 0.5 meters. So that's a small amount. But the black block would have traveled 3.5 meters, a much longer distance. And so now we are gonna calculate the force, the work done by you when we use this equation right here, which is work is force times time. And this is a wrong equation to use, but we're just gonna use it for the sake of explanation. So when we use this, the wrong equation, we're gonna get 1 joule and 1 joule for them. So obviously the joule part doesn't work. Joule is not the correct dimension when you do force times time, but let's just say for the sake of explanation that this is like just what the dimension that we're gonna be using for now. Okay, so it's 1 joule for both, but if we use the correct equation, which is force times distance, we get 0.5 joules for the first for the white block, and for the black block we get 3.5 joules as the work done. And you might be complaining, so this example shows us that if the block is not going at if the initial velocity of the block is slower, then we do less work. And if the initial velocity of the block is faster, we do more work on the block. Because, as you see in the example, if the initial velocity is slower, the distance is obviously much lesser than when the initial velocity is faster. And in fact, that is right. Because work is the change in kinetic energy. When, the velocity, initial velocity of the white block is, slower than the black block, we do less work on the white block than the black block, because the black block has, is faster and moved a greater distance. And you might be like, wow, that's unfair because, it just moved a greater distance. That doesn't mean anything. That's just, it just moved the greater distance because it was already fast. And well, that's true, but that's not true because kinetic energy doesn't work that way. So this is where kinetic energy is important, and we must shift our focus to kinetic energy because, you know, um, in this example, in the first in the case of the white block, the kinetic energy when t equals 0 seconds. So when initially the kinetic energy is let's choose another color. No, actually, let's just go with this color. No. We'll choose the green color. So the initial kinetic energy is, since the velocity is 0, the kinetic energy is 0. And the final kinetic energy is, let's see, yeah, 1/2m. In the case of the black block, the initial kinetic energy is 1/2 m times 3 squared is 9. And the final kinetic energy is 1/2 times n times 16, because 4 squared is 16. So you can see that the difference in kinetic energy, which is work, is 1/2 m in the first case, and 1/2 m times 7, because 16 minus 9 is 7. And this proves that just because the black block was faster than the white block, and it went more a larger distance, the change in kinetic energy or work is greater. And you might be like, whoa, I don't understand. And that is all because, kinetic energy is, the equation for kinetic energy is 1/2 mv squared. It's v squared, right? So obviously, because it's v squared, the bigger the v gets, the more difference it has, although v increased the same amount. And this is all mathematical stuff, but so if you don't understand, just chill. But if you understand, just continue. Right, so it's so it's v squared, so the bigger the v gets, the difference gets bigger. And the reason why kinetic energy is like this, I'm going to explain later. But anyway, so now you know that work must be force times distance, because when some when something goes a longer distance, you know, it does do more work. So now I'm gonna explain why kinetic energy is 1/2 mv squared for those who are curious. So this is actually something I got from the internet. So this example is quite easy to understand. So if you have a person that jumped down from a cliff that's going down, you are gonna have we are gonna have each of these as 1 meters. Okay, so there's 4 1 meter span, uh, and if say if you since there's acceleration from the gravity, you are gonna accelerate, and your velocity of going down will be faster, and you're gonna fall faster, faster, faster. And since you fall down faster, there is less time for you to accelerate during this span, because you spend less time during each 1 meter span. Since you are moving faster, you have less time to accelerate, which means that the change in velocity, the change in how many meters you go per second, matters more and more when you know you increase in velocity. So it only makes sense for kinetic energy to be v squared, since as the velocity gets bigger, acceleration won't be very effective on the same distance. So as the velocity gets bigger, it must the change in velocity must be of bigger importance. So kinetic energy is 1/2 mv squared. And this all leads back to the fact that, you go more distance, um, you have a you have done bigger work. All right, so that's it.